Hi everyone, welcome to Technology and Programming for Mathematics. I wanted to talk a little bit today about recursive functions in Python. So what I wanted to start with was the Fibonacci sequence. So I'm sure you know what this is already, but just so we're all on the same page, the Fibonacci sequence starts out with two ones, and then the third term is the sum of the previous two terms. So 1 plus 1 gives us 2, and then we follow that relation from here on out. So to get the fourth term, we do 1 plus 2, which gets us 3. 2 plus 3 gets us 5. 5 plus 3 gets us 8. 5 plus 8 gets us 13. 8 plus 13 gets us 21, and we could continue doing that for as long as we like. If we write down a little subscript notation for the sequence, let's use F for Fibonacci sequence. F1 is the first term, so F1 is 1, F2 is also 1, and Fn, in general, the nth term in the Fibonacci sequence, is found by taking f sub n minus 1. Notice the minus 1 just applies to the subscript, not to the value of the term. So if you want to find f5, which is this right here, you take f4, the fourth term, plus f3, the third term. Take the values of those two, add them together. So that is our recursive definition of the Fibonacci sequence. And when I say recursive, I just mean that the subsequent outputs depend on previous outputs from this process. Okay, so what I want to do is I want to write a Python program that will find the first Fibonacci number that is bigger than 1,000. Okay, we can see that the Fibonacci numbers are increasing, they're growing. So, and in fact, they're going to be growing faster and faster. So there will eventually be a point in time where I'm writing down numbers bigger than 1,000. So I want the computer to figure out when that is going to happen. So my program is going to have a couple of components. I am going to have a function for generating the Fibonacci sequence. A function for generating terms in the Fibonacci sequence. And then second, I will have a loop that produces terms in the Fibonacci sequence until those terms are greater than 1,000. So let me switch over to, oh, I turned myself off. Let's just turn the document camera off for right now. Okay, so I've got my program right here. So let's focus up here for a sec. Okay, I wrote a little function that will take a integer, a natural number, as its input, and will return that value in the Fibonacci sequence. Okay, so in other words, if we go back to our written values right here, if I put in, let's say, 8 into this function, I want the function to give me term 8 in the Fibonacci sequence. which is 21. So I want the function to spit out 21. Okay, so, well, how do we get the 21? Well, we take the 13 and the 8 and add them together. So how do you get term number 8? You take term number 7 plus term number 6. So as you can see here, in our definition, the function's name is fib. I'm using the function structure in Python that starts with this keyword. I'm defining a function, and I'm calling it fib for Fibonacci. So you can see here, if n was equal to 8, then it would compute fib 7 plus whatever it gets from fib 6. So this is a function that calls itself. It's a recursively defined function. Now, when I was writing this program, I wanted to make sure that what I was doing for this function was correct. So I put this little bit of code in here just to test it out. Okay, so over here, it's prompting the user to say, which Fibonacci number would you like to see? And let's practice it. Let's say 8. I want to see Fibonacci 8. Term 8 in the Fibonacci sequence is 21. Great, that's what we wanted to see. Let's run it again and find term 9. Now we know term 9 should be 13 plus 21, which is 34. So term 9, 34. Great. If I say, give me term 2 in the Fibonacci sequence is 1. So you can see here I've got an if statement inside my function. If we're finding term 1 or term 2, then the function is going to spit out, the output value is going to be just 1. If you're finding term 3 or greater, then the function is going to use the recursively defined rule. Okay, so let me comment these lines out because I really don't want that. What I want is this right here. So this is the part of the code that is going to find the first Fibonacci number that is bigger than 1,000. So I'm defining my variable n here to be 1, and I'm having the computer calculate Fibonacci of n as long as the output for this is less than 1,000. And what it's going to do is that it's actually going to tell me the value of the various Fibonacci numbers it's computing, and then each time we go through the while loop, it's going to increment n and go to the next value. So, since we're starting with n equals 1, f fib of 1 is 1. That's less than 1,000, so it's going to go through these instructions. And now it'll print this line, and then n equals 2. And then it's going to go through again. And it's going to keep repeating that until the Fibonacci function gives me something bigger than 1,000. So let's go ahead and run the program as is right now. Okay, so we can see here, it actually gives us a nice little printout of the Fibonacci numbers. Okay, so it tells us term 1 is 1, term 2 is 1, etc., etc. And the first Fibonacci number larger than 1,000 is 1,597, and that is the 17th term in the sequence. So you see, you don't really have to go very far in the Fibonacci sequence to get a term bigger than 1,000. So I just wanted to show the class this example of a function that calls itself. Okay? So a very intuitive way to code the rules for the Fibonacci sequence. Now, I do want to show you a bit of a shortcoming for this type of code. So very easy to understand, but it's kind of inefficient. Let me do this. I want to find not the first Fibonacci number that's bigger than 1,000. I want to find the first Fibonacci number that's bigger than 1,000,000. Okay, so I've changed the while loop. It's going to go through these instructions while the value of the Fibonacci sequence is less than 1 million. I'm going to hit run here. See what happens here? See how it's slowing down? 30, okay. So it finally got that the first Fibonacci number larger than 1 million is this right here, and it's term 31 in the Fibonacci sequence. So I just wanted you to see how it kind of grinds a little bit there, even though we're only going to the 30th term. And the reason it's doing that is because every time I call the function, let's say I want it to compute Fibonacci 25, it's got to compute Fibonacci 24 and 23 and 22 and 21. It's got to do all of them over again. Okay? So this is a very quick way to do the coding, but not very efficient. And this is something I showed the class the other day, but if I do a little bit bigger, let's say I add 3 more zeros. So this is 3, 6. Find the first Fibonacci number that is larger than 1 billion. Well, let's watch what happens. It's gonna, we saw it was slowing down around 30. This is going to take quite a while to compute. Okay? Because, as I mentioned, every time we do this, it's redoing every single term and going from scratch. So I do have, so I just stopped it there. It's going to take a while. I do have one program that does find this stuff more efficiently. So let me go to my REPLs here, and Fibonacci for loop. So as you can see in this program, I've defined it a little differently. I still have an if and an else. So if the input is less than 3, in other words, if the input is 1 or 2, then the output is 1. Here I'm doing this little bit of chicanery. We'll talk more about this type of structure in a later project. I call it the switching method. So I define A and B, and then I have a new variable C that's defined to be the sum. But I want to show you how fast this goes. So in the previous program, we wanted to find first Fibonacci number less than 1 million. And so it started to grind there around 30. Watch how fast this one goes. Oh, so much faster, noticeably faster. I haven't tried 1 billion on this. Let's see what happens. Run it. Oh, okay. See? No problem at all. That was super quick. So much more efficient code, but a little less intuitive than the code that we saw in the previous example. So the main theme is we can define a function that calls itself. Okay? That's the punchline, the key idea.